rotational force and rotational inertia, or torque Ni. What we're looking at here is in the overhead of a disc or a gear that could pivot about the triangular shaped wedge. If we apply a force to this disc at the location drawn, well, this disc or gear will rotate. If our initial rotational motion, omega I, is equal to 0, it's rotationally at rest, then this force will cause a change in the rotation. Omega final will not be 0, and it'll rotate in the direction of that curved arrow. So the change in rotational speed, the change in rotational velocity omega will be CW, or clockwise. So if we change rotational speed, the rotational velocity omega, delta omega, if it's changed in some time frame, delta omega divided by delta t, then there must have been a torque applied. We also know that torque is related to a force acting at a distance away from a point of rotation. In that case, our distance is now drawn here as a position vector. The position vector's tail is at the point of rotation, the pivot, where this gear or disc can rotate about. And so the position vector's tail, the position vector's tail starts at the pivot, and the arrowhead points to the tail of the force. It's locating where the force is in relationship to the center of motion. D cross F, vector D cross the vector F, that multiplication product, is equal to the magnitude of d, f, and sine theta, where theta is the angle between our two vectors, our position vector D and our force vector. The angle is drawn as 90 degrees, so sine of 90, or pi over 2, is 1. What if instead we apply the same force, but in a different direction, a direction parallel to this position vector, FB? We know FA creates a torque to rotate this disk. Will FB, the same force at the same location, but in a different direction, in this case parallel to the position vector, pointing away from the pivot point, will that also cause a torque? And will that torque be the same amount, considering the value of the force is the same and the position vector is the same? Well, the torque will have to change because the angle between the vectors is no longer 90 degrees. It's 180 degrees or 0 degrees, which would collapse your torque to nothing. That force B and the force A, although same in magnitude and distance from the pivot, will have entirely different effects. The force of A will cause a change in the motion, a change in omega, and the force of B will simply just pull on the object, trying to move it away from that pivot, but not cause a rotation. So how does the torque B relate to the torque A? Well, the angle is what's important here. What if instead we applied a force C? A force C at a different location, the location of force C, drawn with position vector D2, again from the point of rotation, the center of rotation, or from the possible pivot. Its tail vector T2 from pivot to the arrowhead of the position vector, pointing to where force C is applied. So force C will also create a torque. And if force C is equal to the same force A as force B, well, that torque created by force C at position vector D2 will torque C be equivalent to torque A and to torque B? How do they relate? Is one greater than the other? Well, again, the difference now between FA and FB and FC is the direction of the force and the angle the force makes. The angle theta that's in the torque equation, in the sine theta function, the angle is between position vector and force vector. It's the angle between the vectors. Well, drawn here for position vector 2 to force C is theta 2. So that angle, that greater than 90 degree angle, would be the value complete for sine theta. We could also have used the angle between force C, the smaller angle between force C and what's called the line of action, the direction the position vector is pointing along. In both cases, the sine of either of those angles will give you the same value. What that value is can be thought of as force times sine theta as the perpendicular component to the force, perpendicular to the line of action or perpendicular to the direction the position vector d2 is pointing. That's the component of the force that's opposite the angle that's being drawn. So once we have a force that's perpendicular, whether it's a component of the force or the entire force that's perpendicular to the position vector, we get a maximum torque. And so this is what the torque idea is how does the position vector d and the force relate to each other? How much of either is perpendicular to each other? And lastly, our fourth force, force d, is applied at the pivot. So its position vector is 0. Is the torque that d creates equivalent to torque of A or B or C? Or is there no torque because there's no position vector? Consider these four forces and the torques that they may or may not make. And then rank the torques. How does torque A, torque B, torque C, torque D relate? Submit, turn in the beginning of ill whether torque A is greater than B or greater than C or less than. So rank them by greatest to least. Our next example, let's say I have a person standing on an edge in a precarious position, shown here standing on this pivot. Say they're trying to balance themselves. Well, if they tilt one way or the other, they'll fall. As you know, one way that makes it easier for yourself to not fall is to lift up your arms. Why does this work? Well, it's also a story of torque and rotational inertia. Drawn there is your center of mass. Earlier, your center of mass was low when your arms were hanging low. When your arms were raised, your center of mass went to a higher position. So now if you tilt, you're less likely to, you take longer time for it to tip over. Your change in your motion is less. So why is this? This is a story of rotational inertia I. As you know, the rotational inertia I, the moment of inertia, relates to the mass and the location of the mass, d. Once again, d is the position vector, drawn tail from the point of rotation, the head of the position vector, locating the mass, in this case the center of mass that we're analyzing. So from pivot point to the center of mass, that position vector has grown from low to high. So I is related to that position vector, but to the square position vector. So where the mass is, or the center of mass of the person, greatly changes the rotational inertia. As distance increases, it goes to the square. So the rotational inertia, the moment of inertia I, greatly increases. Which means the more rotational inertia you have, the harder it is for you to tip. Now, a force acting on that mass will cause a torque, of course. What force acts at the center of mass? Well, the weight, the force of gravity, mg. Your weight in our model acts at your center of mass. Your force of gravity is acting at a position away from the pivot point, so that's creating a torque. It's the same position away from the pivot point as the mass is located, namely the same position vector d. So d cross F, once again, is the torque, your weight at that center of mass. So that would torque you to tip you over. And again, we can apply the same relationship where the angle between the weight, the force of gravity, and the position vector theta is drawn there. So as your center of mass increases, your position of your center of mass from the bottom of the base of your feet in this case, the position vector located in the center of mass has grown as you raised your hands from a low to a high. So as that position vector d has grown, the torque has also grown. Both the rotational inertia and the torque have increased thanks to the position vector increasing in their equation. Well, we know torque relates to moment of inertia times the change in rotational motion. As we just saw, delta omega over delta t, which is what alpha is, a rotational acceleration. So both the rotational inertia and the torque increase as the center of mass is raised to a higher position vector d from the point of rotation, the base of the feet. Well, again, alpha is the rotational acceleration from rest to tipping over. Well, if your hands are higher, it takes longer for you to tip over. So again, alpha is our change in motion. Our change in motion will be less with the hands higher. So the question is the rotational acceleration when your center mass is low, when your hands are at the lower position, is that less than, equal, or greater than your rotational acceleration alpha when your hands are held high? That's what the answer that you'll submit. The second answer you'll submit at the beginning of the ill. And again, you already know the answer. You raise your hands high, so it takes you longer to tip. You can set up the solution to show that alpha is proportional to torque divided by I divided by rotational inertia, and torque is related to d times weight times sine theta. That would be divided by I md squared. But since they both depend on the position vector, does that mean alpha is going to be the same? More or less. But you know that it takes longer to tip when your hands are high, and this relationship of torque to I relating to alpha can explain why. So that is what you'll turn in.